Okay, so I want to introduce this concept of the mole. Okay, and again, it's how we count. It's got nothing to do with a little furry animal or the rodent. The mole, it's our counting mechanism. Okay, again, ones is too small. Counting by hundreds or millions, counting by dozens, will still give us too big of numbers. Okay? And this is because there's a very large amount of molecules even in an everyday amount of substance. Okay? When we count by moles, we get nice everyday masses that make sense. Okay? For water, and we'll do the calculations later, 1 mole of water is a little over 18 grams. Okay? So I have a little over 18 grams of water in this test tube, and that is going to be 1 mole of water. So a mole is 6.02 times 10 to the 23 molecules. That's what would be in here, and it's a mole. Okay? A mole of any substance in the periodic table is going to be somewhere between a couple grams and maybe 200. Okay? Nice numbers for us to work with. Nice everyday realistic numbers. Now, what Avogadro used to define, what exactly is a mole going to be, he used carbon-12 for his definition. Okay? So he took 12 grams exactly of carbon-12, and he figured out how many individual carbons was that. Okay? And that number became how we defined a mole. And because Avogadro did the work, his name went with this work. And he found out if you have carbon-12, okay, so carbon-12 is the one isotope of carbon that has 6 protons, because carbon always has 6 protons. It's neutral and has 6 electrons. Okay. And the 12 version has 6 neutrons. Okay. Not every form of carbon has a mass of 12 and has 6 neutrons with no charge. Okay? But that's the isotope that he was counting. Okay? 12 grams of that isotope happens to be 6.02 times 10 to the 23 units, okay? Or in this case, carbon. Okay? I'm using the word units because we can count anything by Avogadro's number. We could count people and say how many moles of people are there on the Earth. Okay? Now, there's only billions of people on Earth, so it would have a very small molar amount if we counted people that way. I'm going to write out this number once, not in scientific notation, okay? And you'll see why we use scientific notation. Okay? So this would be 602, and the 23, to go back to a regular number, means I got to move this decimal place 23 times to the right. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That's Avogadro's number. Okay? Now, I don't want to ever have to do that again. I'd make mistakes just trying to write it out that way. Okay? Every 3, I'm going to put a comma just to help our eye. I can't even say that word. I don't even know what the words would be. 3 zeros is a million, billion, trillion. I don't even know what comes after trillion. And it's so many orders of magnitude bigger. Okay? So it's kind of a number that's hard to comprehend. That's how many water molecules are in this small amount of water. That's why Avogadro's number is so big, and that's why we have to count by a number that's so big. When we deal with counting atoms, we have these unreal numbers. And the other time that you get these kind of unreal, hard to comprehend, I can't even really comprehend how many that is. It's such a bigger number than I ever deal with. And the other time we get really big numbers that it's hard to comprehend in science is space and the solar system. The distances are so big. I know my brain can't really comprehend. The size of the Milky Way is so big, the galaxy we live in, I can't even, it's hard to really get an appreciation for how big that is. There's nothing I can really compare it to. So unfortunately, it's hard to give a really good perspective of this number. Okay? But it also lets me, do that quick recap of scientific notation. Okay? This 23 is really counting places of 10 or times 10. Every time we move a decimal, it's a 10 times factor. So I've moved the decimal from after the 6, where it was, 23 times. Okay? Now, I didn't put it in. We typically don't put a decimal at the end of a number, okay? But that's where it is. Okay? And there should be 23 jumps where I made a mistake getting this number out quickly, but I think I did it correct. Okay? So that's what we're going to count by. It's so much easier to say, I have 1 mole, than to say that number. It's so much easier to have 2 moles of water than to double that number and use that language. So you're going to do a few calculations of actually counting the units, but it's not going to be a big deal on your unit test. So let's, we need to be able to do some calculations with this. So a little bit more vocabulary, terminology, so we speak the same language. So we're talking about mole. The term that goes with this, particularly next year in Chem 20, is we call the mole the chemical amount. Okay? If you ever have a question that says, what is the chemical amount of water in 100 grams? Okay? They mean moles. Okay? Amount is just counting. What amount do you have? But we want it in moles. We don't want it in mass. We don't want to count by dozens or hundreds. Okay? It's given symbol N, which might seem a little weird. Why would you give it symbol N? Okay? Now it's unit or mole, just M-O-L. Okay? Now little m was taken for mass already. So we can't use little m, that's out. So little n was picked as its symbol. Okay? And you'll see me use n in formulas meaning moles. Okay? My second slide is a bunch of graphics. You're not going to write this down. Okay? This is a picture of a whole bunch of chemicals that are exactly 1 mole. Okay? So we have our carbon. Okay? 12 grams of carbon is a mole. Okay? By definition, it has to be carbon 12, but even any form of carbon is pretty close to 12. Zinc has more neutrons and protons in it. So when you add up a mole of zinc, it's a bit heavier because there's more in the nucleus. So zinc's a bit heavier for a mole. Okay? Magnesium, 23 grams. Copper, almost 64 grams of copper to get a mole. Sulfur's 32, silicon 28. Okay? When you get lower in the table, okay, if we get down to lead, atomic number 82, 82 protons, okay? Well over 100 neutrons. Okay? When you count up a mole, there's a lot more mass compared to the other atoms. And you're well over 200. Okay? Getting up around the higher end that you'll see. Okay? Now, often in this course, we're not going to use a lot of these lower down metals, or particularly the ones way at the bottom. We're going to be in the first 20 elements. So we're going to be between 0 and 50 a lot of the time with the elements we're going to be using. Okay. So next I want to teach you how to convert. How do you go from moles to how many units you have, or if you know units, how do you go back to moles? Okay. Okay. Converting between units and moles. Okay. You need Avogadro's number to go between the 2 variables. We've got Avogadro's number, that's a constant. That's 6.02 times 10 to the 23 of anything is a mole. Well, that's not going to change. The amount of moles you have could change, which would affect the total count that you have. And we're going to work through a couple math examples in a second. So I have 3 problems. How many molecules? Okay. So I'm still talking about individual units. We can count atoms or we can count molecules. They're still the individual units. Okay. When I say a water molecule, that would be 1 water molecule. Okay. If we had 3 moles of these, that'd be 3 Avogadro's numbers worth. We're going to figure out how much that would be. What if you had 5 moles of something? And then last, what if you had a number less than 1? Okay. Less than 1/10 of a mole. How many would that be? Is everyone okay hiding the top? Good. Okay. So first, we need to get a strategy or a formula that's going to get us to let us do some calculations. We're going to turn this into some symbols. Okay. We've got Avogadro's number, okay, times mole. Okay. When we write formulas, we tend to just use the symbol. It's shorter, it's quicker. That's what you see in formula sheets. Okay. What was that 1-letter symbol for the mole? Pardon? N. Okay. So Avogadro's number times the number of moles is going to equal the count. Okay. And I'm just going to put a C for count. And we could be counting anything. Okay. So I want to figure out how many water molecules. I want to do a count. Okay. So that's what I want to get. Okay. So I don't have to do any rearranging. Okay. To get the count, Avogadro's number times the number of moles will tell us how many there are. Okay. Again, you can count anything, and I'm going to be counting molecules. So I need to take Avogadro's number times moles, 6.02 times 10 to the 23. Okay. I'm going to multiply that by 3 moles. Okay. Now, I didn't put any units in for Avogadro's number. This is 6.02 times 10 to the 23. Whatever we want to count is in 1 mole. Okay. Per 1 mole. Whenever we say per something, it's always a denominator. It's on the bottom. Okay. Same if you go kilometers per hour, what comes after the per goes down below the fraction. So I'm doing the same thing. So 6.02 times 10 to 23 molecules if we're counting per mole. Divide by moles. Okay. Multiply by how many moles we have. Okay. I shouldn't have dropped that 0. Equals, now I grab my calculator and have to do this calculation. Okay. And that works out to 1.8 times 10 to the 24 molecules. Now, how many in here have one of those TI-83, 84 calculators? Okay, only a few. Okay. Now, whether you have those or not, most of the calculators have a shortcut for this times 10 to the power of. Okay. Now, I'm going to have to help people individually because everyone's calculator is a little different. Okay. Some of them will actually have a little times 10 button. Okay. Most of them, including the TI-83s and the 84s, just have an EE button. Okay. It kind of seems weird. It doesn't make a lot of sense, but that's what Texas Instruments put on their calculator. Okay. So to input this scientific notation number, for most calculators, you go 6.02. Okay. And then you either hit this button on your calculator, or for most, it's an E, double E or single E. Okay. And your calculator will just stick an E in, because often your calculator screen can't write scientific notation. Okay. So 6.02, find one of those 2 buttons in your calculator, and then you put in the power. And that's how you input scientific notation. Okay. Again, between today and Monday, see me in Pride right after school and make sure you're good with your calculator. If you're not, Okay? And many of you might be okay with that. Okay? A good double check when you're doing these calculations is I started with more than a mole, so I should have a number that's bigger than Avogadro's number. And I do. I'm 10 to the 24. Okay? 24 digits now instead of just 23, or more digits. Okay? A bigger number. Okay? B, okay, is going to look very similar. Okay? Now we're trying to do 5.5 moles. I'm just going to write this out and then I'll get your 6.02 times 10 to the 23 molecules per mole, that's Avogadro's number, times 5.5 moles equals, and you had a question? Can you just, if you really have to, you can. So now we've got an even bigger amount of moles, so we should be getting an even bigger scientific notation number, okay? A bigger power potentially, or at least this part getting bigger, and it works out to 3.3 times 10 to the 24 molecules. Okay. So this is bigger. It's the same number of digits, which comes from the 24. So the length of the number is the same, but the first numbers are 1.8, and now they're a little bigger at 3.3, okay, which makes sense. Okay. My last example, C, I did it because I picked a small amount of moles. Avogadro's number, 6.02 times 10 to the 23 units per mole times our moles. Now we have a count, and that's all mole is counting. That's much less than a mole. That's less than Avogadro's number. So we should get an answer that's smaller than Avogadro's number, or we've made a mistake. And this one comes out to 3.7 times 10 to the 22 molecules. The first place you want to read in figuring how big it is look at the power. Okay? 22 versus 23. Okay? The 23 power is a certain length of number, so many digits. There's actually 24 digits in that number. This one has lost a digit. It's got one last number, one last zero. That's smaller. Okay? So look there first before you look in front. Okay? Yes, this number 3.7 is slightly bigger than 3.3, but there's a whole less digit. Okay? It's kind of like comparing 10,000 versus 1,000. There's one less zero. Okay? There's one less zero there. Okay? So that's how we calculate how many molecules there are. Okay? This skill, I need to teach it to you. It's a little less important than what I'm going to do after this. Okay? So I'm only going to put this on the quiz that you'll get next week. I won't put it on the test. Okay? But everything past here, past this slide, is really important. Will be on the test and the quiz. Okay? I just have one more example, and then we'll move into the more important material today. Okay? Still doing counts, but we're going to work backwards. I'm going to give you the count and turn it into moles. It's the opposite. How many moles of water are in, and I give you the count. Okay. I'm going to scroll up for 1 second. I know many have started to write. Okay. This first, how many moles? Okay, we were solving, how many moles? We were just solving for count. Okay. Now we're going to know count and solve for moles. We're going to have to rearrange this because we're solving, this is going to become our question mark on the bottom. And just 2 examples this time instead of 3. How many water molecules are in 1.2 times 10 to the 24 molecules, or 5.1 times 10 to the 23 molecules? Okay. So I'm going to turn our theory back into the formula that we started with. We've got Avogadro's number, which is something count per mole divided by mole. Okay. We then multiply that by mole. Okay. Okay. This is some sort of count. Now there's some count per mole. We're going to multiply by mole, and then our mole on the bottom cancels our mole on the top, and that's going to equal our count. Solve this question. I want to rearrange this and get mole all by itself, so I can solve for moles. Avogadro's number times, I'm just going to use the symbols now, N equals our count. But I want moles. I want that all by itself so I can solve for it. I don't want to have Avogadro's number next to it, so I want to get rid of it. Okay. I want to cancel it out. Okay. So you want to do the opposite operation to cancel or get rid of something next to it in a formula. Moles is being multiplied by Avogadro's number, so the opposite operation would be dividing by Avogadro's number. And that'll cancel the top and the bottom. But when you have an equal sign, whatever you do to one side, you have to do to the other to keep the equals. Now the point of doing this, this number will cancel that number out. If I had 5 on the top and I do 5 divided by 5, they cancel each other out. Or if I have Avogadro's number divided by Avogadro's number, they cancel each other out. So this is what we're going to need to do. We've now moles all by itself equals count divide by Avogadro's number. So you either have to do this rearrangement yourself or remember this. I'm going to do A. So number of moles is count divided by Avogadro's number. The count is 1.2 times 10 to the 24 molecules. Divide by Avogadro's number, 6.02 times 10 to the 23 molecules per mole. And that will tell us how many moles we have. And before you even touch your calculator, let's make a guesstimate. Okay, this will help, again, correct your errors. Okay, do we have our molecule count? Is that bigger than a mole or less than a mole? It's bigger, okay, to the power of 24 versus 23. We better get a number greater than 1. If we don't, we've made an error. We've got more than a mole. We've got more molecules than what's in a mole. Okay, so we should get a number bigger than 1. Okay. When you divide those two out, it works out to 2.0 moles. Okay. So that's a good sign I've done this right because we know we've more than a mole. B, the moles, okay, same strategy as the count, divide by Avogadro's number. Okay, in this case, we're counting molecules. There's 5.1 times 10 to the 22 molecules, which is what we're counting. Divide by Avogadro's number, okay, which is whatever we're counting, divide by moles, and we're counting molecules. The molecules cancel out. We're just left with moles. I want to do the same thing. Okay. Is this number bigger than Avogadro's number like before, or is it smaller? It's now smaller. Power of 22 versus Avogadro's number has 23, 6, and then 23 digits before you get to the end. This has a 5 and then 22 digits, okay, be it a 1 or a bunch of zeros. Okay, so this has one less digit, okay, which is like 1,000 compared to 100. Okay? There's one less digit in 100. So less than a mole, so less than Avogadro's number, so we should get less than a mole. And I got 0.085, okay, a fair bit less than a mole. So again, this is your first skill. This will be on your quiz number 2, but not the exam. Okay. I want to see if you can do it on a quiz, but it's not, I'm not prioritizing it for the exam. You're not going to do this again in high school, which is why I'm not going to prioritize it. Okay. The next skill you use all 3 years. So we'll finally move on to what's super important, molar mass, and figuring out the mass you have. Okay, I never am going to care about how many actual individual molecules are in here within chemistry. It's not useful, but I will care about moles and I'll care about mass, that conversion, not count moles, mass moles. Okay, we need molar mass to do that. Okay. It is now not the count in a mole, it's the mass of 1 mole. Okay. So molar mass is mass per mole. That's going to be our units. Okay. And that's basically, I'll put up a formula, but the formula is just those units. Molar mass equals mass divided by moles. Okay. Okay. Given symbol capital M. Okay. Little m is mass. Okay. Big M is mass per mole, molar mass. Okay. Now, how do we, one way to get molar mass is it can be determined by adding up the average masses. That's these numbers on the table. These are all averages for planet Earth. Okay. On Earth, the average mass of hydrogen is 1.01. The average mass of oxygen is 16.00. Okay. Then if you're doing a test or quiz, particularly the gentleman and lady up close, don't use these numbers. Use the numbers right in your table. They're slightly different, and when the words I'm saying are the ones in your booklet, okay, not the ones here. Okay. Every source is slightly different. Okay, so just add up the mass of all the individual pieces. This is how you'll get molar mass. Okay. So this is a skill you're going to be quite successful at. Okay. So let's do that a few times. I'm going to do it 4 times, and then we'll figure out, well, how can you get moles if you know the mass and the molar mass. So my first example will be water. What is the molar mass of water? Okay. Okay. This is 1 mole. You know, we'll figure out how much it weighs. I've said it, but we're going to actually figure it out. We got to add up the mass of all the atoms. So let's make sure we're very clear on the atom count. Hydrogen has how many atoms in water? 2, okay, coming from the subscript. Okay. Oxygen, there's no number after oxygen, so there's just 1. So we have to add up 1 oxygen and 2 hydrogen. Okay. Okay. Numbers in front don't affect molar mass. This just means there's 2 water. Okay. But water has 2 H's and 1 O. Okay. So we're going to ignore any numbers in front. If you ever see that, it doesn't affect the molar mass. That's just a balancing thing. It's not what water looks like. So we've got hydrogen. I'll do that first. We've got 2 of them times, you go to your table and you look for, it's not labeled with any units. On this table, it's right below the symbol. I think it is, yeah, it's right below the name in your data sheet. Okay. So you have to realize that decimal number is the molar mass in grams per mole. Okay. So what is it for hydrogen? Perfect, 1.01, and that is grams of hydrogen per mole. For oxygen, there's one of them, times oxygen, I mentioned a second ago, is 16.00 grams of oxygen per mole. Okay? And we need to add those two numbers up. Okay? Double the hydrogen plus one of the oxygen. Okay? A lot of students will do this right on their calculator. They'll just look up hydrogen, double it, plus one oxygen, and not write anything down but the answer. Okay? But as a teacher, you can't teach like that. I've got to show you all the steps. Okay? Most of you will skip these. Okay? And this works out to 18.02 grams per mole. Okay? I've done water so many times, I don't add it up. I just know what it is. By the time you finish grade 12, you'll probably just remember this number because you'll do water so common. So that is the molar mass, the mass of 1 mole, and that's where that 18 grams came from in my 1 mole. Okay. Let's do methane. No number after carbon, there's 1 of them. Hydrogen, there's 4 of them. Okay. Now I'm going carbon dash 1. That's not a negative. I'm just putting a dash in. Okay. So carbon has 3 isotopes, but the average of all the isotopes on Earth is 12.01. That's the number in your data booklet. You just go to carbon, find that bottom decimal number. There are 4 hydrogen, which we've done hydrogen already. And I've got to add up. Do the multiplication and then add up all the pieces. And this one is 12, 13, 14, 15, 16.05 grams per mole. Okay. Methane, the molecule is a little lighter than 1 molecule of water. Okay. A mole of each of these is the exact same count, okay, but water is heavier. A mole of it is heavier. Okay. 2 more. Copper, elemental copper. Okay. All the metals in their elemental form are just 1 of them. Okay. So that's why I have copper and nothing else. I could have put the state in. I left it out at first to try to be as clear as possible. But I'll throw that state in, but there's no subscript after. So I just need 1 of them. Okay. I'm not even going to write out the count. There's just 1. So I've got to find copper, and it's just 1 of them. So it's just that number. Okay. The molar mass is the atomic mass, the mass of 1 atom. So for copper, that's 63.55 grams per mole. Okay. That's the mass of 1 atom. That's the mass of the formula unit. Last, we have diatomic oxygen. This is how oxygen comes naturally. The oxygen in this room is all in pairs, okay, and that's why we're breathing. Okay. So our O count is 2. So our molar mass is 2 times 16.00 grams per mole, and that's 32.00. This is another one you'll do a lot over the next 3 years. Every time you do a combustion reaction and you're doing calculations, you'll have oxygen as the other reactant, and you'll need its molar mass. Any questions about molar mass or what if, the situation, you're not sure how you deal with it? I'll set up one last example. I'm not going to do it, okay, but I'm guessing the questions can just get longer, but not really harder. Okay. You could have ammonium is a positive ion, And you could have ammonium nitrate, NH4 plus, NO3 minus, plus 1 minus 1. So that formula unit is balanced, and I could ask you for the molar mass. And it's larger, there's more types of atoms, but you just have to count them all up and then add up the mass. Nitrogen, how many total N's are there? Not one, two. There's one here, and then there's one in the anion. So there's two in total. So I double nitrogen, which is 14.01, I think. Hydrogen, there's 4 here, and there's none over there. So 4 in total. Oxygen, there's 3 there. There's none anywhere else, so there's 3 of those. Okay. And if something's negative or positive, it doesn't matter. Losing or gaining electrons doesn't affect the mass. They're so light, it doesn't affect it. Okay. So ions don't do anything different if something's ionic or if you just have an ion. Okay. I'm not going to add that up, but you have the count. Hopefully you'll be successful in getting the molar mass of a compound like that. Okay. So that's getting molar mass. Okay. But what we want to be able to do is to go from mass to moles, or moles, mass to moles, or backwards. Okay. So I want to do this conversion. And we're getting near the end of today. Okay. Determining moles from mass will be our theme of this slide. Oh. You can either just track your units or make a formula out of the units. We've got molar mass, which is big M, and that stood for 2 things. And if you remember its units, we basically have made a formula out of really tracking units. So what were the units? They're in front of you, but try not to look down, but you can if you forget. What was molar mass? What was on the top? I think grams or mass. Okay, so grams is a unit. The symbol is mass. Okay. And what was on the bottom? What was the bottom unit? And I'll use the symbol that goes with that unit. Mole, and mole we use a little n. So you'll see this formula. I'll use it in Chem, in Science 10, in Chem 20, in Chem 30. Okay. And it's just coming from the units. If you remember grams per mole, you can get the formula out and then rearrange it. Okay, we just learned how to solve for big M, and now we can really solve for any piece as long as we can rearrange the formula. Okay? You can figure that if I say it's water, okay, you can figure out the big M. Okay? And then I have to give you one of these two. So I have to tell you the chemical. You find that out on your own, and I must give you another piece, so there's nothing you can do. Now, I'm going to do a question. What is the mass? Okay. Mass is going to be my question mark. We need to find out. Well, that formula doesn't have a little m all by itself. We've got to manipulate it. Okay. There's several ways to do this. You may do this a different way than I do, and great, you know what you're doing. Okay. I'm just going to pick one way. Cross-multiplying is one of the simpler ways to manipulate this formula. Okay. I'm going to take the top of one side and multiply it by the bottom of the other, and then go equals the other cross, or the other diagonal I did in red. Okay. So if I take big M, it gets crossed with nothing on the bottom. So we just have big M, okay, or 1M. We're really multiplying by 1. Which doesn't change the number. So one cross is just our M. The other one is molar mass times moles. And that ends up getting us what we wanted. Okay, so I don't have to keep manipulating that formula. And when we put our units in, they're going to work out. Molar mass is grams per mole. We're going to multiply by moles. Moles on the top will cancel moles on the bottom, and we'll get grams, which is good because that matches with mass, which is what we want to solve for. Okay? So please get used to putting your units in and canceling them out. And when you rearrange a formula incorrectly, maybe you'll catch yourself. Okay? If you ever had grams multiplied by grams, they're both on the top, they don't cancel. You get grams squared. It means you have a formula that's incorrectly rearranged. Okay. So I'm going to do those 4 same examples that we did before. We've already solved for molar mass, so it saves us that step. Okay. So what is the mass of 1 1/4 moles of each? So I want to get, what is the mass of 1 1/4 moles of water? Now this is 1 mole, so we're talking about a little bit more. It better be a bit more than 18, because this is 18 grams for 1 mole. Okay. What's the molar mass of water? We did that. The mass of 1 hydrogen and 2 hydrogen and 1 oxygen, it's just a little below, is 18.02. Okay. So I'm not going to repeat that. Okay. So you're going to keep flipping back to the slide we just did. 18.02 grams of water per mole. Multiply by moles, we're asked 1.25. Okay. Forgot my units. I have moles on the bottom, which will cancel moles on the top. So my units, that I have a G on the top that hasn't canceled. So that's where units in your answer come from. They're the units that did not cancel. Okay. 18.02 times 1.25, 22.5 grams. Makes sense? That's more than the 18 that 1 mole would weigh. I'm going to do 1 more, and then I'm going to have you do the bottom 2. Methane. We want the mass again, which is molar mass times moles. That's coming from my work I did up here in rearranging my formula. Okay. Methane has a different mass. 1 carbon and 4 H's was a little less than water. 16.05, I believe. Yes. Again, we're doing 1 1/4 mole in all of these questions. Again, same unit cancellation. Mole on the top, mole on the bottom, gram didn't cancel. So that's the units of my answer. And this one is 20.1 grams. A mole and 1/4 is a little less for methane than it is for water. 2 left. We have carbon and oxygen gas left. And see if you can compute what the mass of each of those would weigh. 1 1/4 mole of copper and 1 1/4 mole of oxygen. I'll scroll down in a second once I'm sure everybody has those top notes. Okay. So for the copper, the mass was 79.4 grams, and for oxygen, 40.0. I'm going to talk about why a lot didn't put in that decimal 0, and I want to just address that now with significant figures. And in physics, you're going to get a lot bigger discussion on significant figures. We haven't done a lot of calculations, so I haven't talked about it yet but I'm going to address it a little bit right now. Okay. So for oxygen, you had 32.00 grams per mole. Okay. And those 2 zeros come from the fact that your data booklet was to 2 decimal places. Okay. So you had to keep those 2 decimal places when you added the 16.00 twice. And then you multiplied that by 1.25, which was stated in the question. Okay. Our units canceled. Okay. And then I need to recap, how do you decide how many digits to put in when you do a multiplication? Okay. And the rule is the same as division. Okay. So I'm talking about significant figures, okay, which is, significant is a measured digit. How many measured digits should you put into your answer? Okay. If you are multiplying or you're dividing, okay, adding and subtracting have different rules. Okay. If you multiply, you divide, you're going to keep the lower significant figures. Okay. So basically, you're only as good as your worst measurement. So in science, there is no point, weighing out how much water I have on a $10,000 scale that gives me 5 significant figures, okay, if I'm then going to do a calculation with that and the next measurement only has 2 sig figs, okay, or 2 measured digits. Okay. You want to keep them similar ideally. Okay. In this case, this number has 4 significant figures. The 3, the 2, and then the only reason to put zeros at the end of a number after a decimal place is if you measure them. Okay? If these were not measured, you wouldn't write them in. Okay? Okay? So that is 4 measured digits, and this has 3 significant figures, which is just how many measured digits do you have. Okay? There was a 1, a 2, and a 5. Okay? So there's 4 here. There's 3 on that side, so I'm going to keep the lower of the 2. So I'm going to keep 3 would be the lower. So I'm going to keep 3 measured digits. Okay. So the first one is the 4, then a 0, and then a 0. All 3 of these are deemed to be measured digits, and they just happen to come out to zeros. Okay. Zeros way at the end of numbers that have decimals are significant. Okay. The big problem with significant figures is counting them when they're not zeros is easy. It's just if it's a 1, a 2, a 3, a 4, a 5, a 6, a 7, 8, or a 9, it's a measured digit. That's pretty clear. It's the zeros, when do they not count? Okay. Zeros way in the front, ahead of a decimal, aren't significant. Okay. So if I had 0.05123, okay, and that's going to be meters, let's say. Okay. Zeros way at the front are just placeholders. Okay. They're just there to keep this 5 in the hundreds place. Okay. Okay. Zeros way at the end are there because they're actually measured. Okay. If I switch units, insignificant zeros, non-measured zeros just go away. Okay. I'll switch this to centimeters. This would be 5.123 centimeters. Those unmeasured zeros just went away. Okay. When you switch to the units, okay, I went from base unit to centi units, those non-measured zeros would disappear. Okay. A measured 0 would always stay. Okay. These are just here to keep the decimal in its right place. Okay. Now again, in physics, you'll have a much bigger discussion about this than you do right now. Okay. When you add or subtract, you don't count significant figures. You keep the least precise digit. Okay. You keep the lower amount of decimals. Okay. Or decimal places. So if I was adding, if I was adding 2.15 okay, to 1.476, You just want to keep the one that has the lower amount of decimal places. That's how many places you'll keep in round 2 in your answer. So I've got 2 decimal places in the top number. I've got 3 in the bottom. So I'd keep the lower. I'd round it to 2 decimal places, which is why I like to write it above and below. Okay? Most of the time in chemistry and physics, you're multiplying or you're dividing, and you're just counting, you know, how many measured digits in each number and keep the lower amount. If you multiplied 3 numbers together, you'd still do the same thing. How many significant figures or measured digits are in each number and keep the lower amount of the 3 as opposed to the lower amount of the 2. So start working on that. I'm not going to be assessing you on that, but I'll give you feedback. You might see SF on a test, means your significant figures are off, and you still might see 2 out of 2 on the question. Okay. Now in physics, there'll be a much bigger emphasis put onto that. You're going to do calculations the whole time in physics. Okay. One last slide, and you're done. Last example. Okay, not new material, just another example for you. A sample of nitrogen dioxide gas has a certain mass. Okay. Determine the number of moles. Okay, that's what we're just doing. And then I'll go back to the start and figure out how many molecules that would be. So I'm tying kind of the whole day in to get together. So I'm going to need a strategy first. I have to see what information I have and need to get to. Okay. I have mass, and I'm trying to get the number of moles first. Okay. I'm going to ignore the molecule part. That'll be my second part. Okay. And that's N. So I need a formula, a strategy that has mass and moles in it. Okay. And that is when we use molar mass that we just did. Okay. Molar mass, which we have to figure out, but it's a constant for any chemical. Okay. So we can figure that out because we know the formula. Molar mass equals, you just need to know its units. It's grams per mole. Grams, which is mass, per mole, which is little n. So I can solve for its moles. Okay. Mass per mole is a little bigger and clearer. So I've got to play with that formula to answer this mole question. I'm going to manipulate that. We'll cross multiply and then keep manipulating it. Molar mass is mass per mole, gram per mole. That's how hopefully you'll remember that. I want to get little n by itself. I'm going to cross multiply first and then get it by itself if it's not there already. Okay. So big M is crossed with nothing, and we get big M times little n. Okay, we did that before to get the little m by itself. But I'm not quite where I want to get to. There's little n. I want it all by itself. Okay. I need this big M moved to the other side. Okay. And I have to do it mathematically. Maintain the equal. Okay. These are being multiplied together, so I do the opposite operation, which is divide by big M to cancel it out. Okay. So I have to divide this side by big M. And now I can solve for moles. And it's the first time you've seen me go solve for moles from math. You've seen all the possible ways to rearrange this formula now within this course in Chem 20 and Chem 30. Moles is mass divided by molar mass. Okay. This is mass, which is just grams. That's molar mass, which is grams per mole. And I'll just keep going. I need mass. Well, that's given to me, 22.3 grams. Divided by the molar mass. Well, we need to figure out, well, how much does one N and two O's weigh? So I've got one N, 1 times 14.01, I believe. Yeah. Okay. A little over 14 grams for every mole of nitrogen. And then I got 2 oxygen at 16.00 each. And I've got to add those 3 pieces up, the 1 N and the 2 O's. And that comes to 46.01 grams of N2O. Sorry, NO2. I said that backwards. NO2, 46 grams of NO2 per mole of NO2. Okay. Now we end up with a gram on the top and the bottom. We end up with moles on the bottom twice, which is mathematically equivalent to just having them on the top. Okay, but you're not used to doing that. You might have to just trust me that when you have moles on the bottom twice, it's the same as being on top. Okay. Before I grab a calculator, we can guesstimate the moles. Okay, 1 mole is almost 50 grams. We have way less than 50. We have way less than a mole. So we should have, you know, a number less than 1. And it's going to be 0.4. Okay. Now that's one of those front zeros that doesn't matter. I've got 3 measured digits on the top. I've got 4 on the bottom, so I want to keep 3 measured digits. 4, 8, and then I round it to 5. A little under half a mole is in 22.3 grams. Okay. Last, figure out how many molecules I have. So I'm going way back to the start. To go to molecules, you need Avogadro's number, that big 6.02 times 10 to the 23, times by how many moles do you have, which we just figured out. So 6.02 times 10 to the 23. In this case, it'd be molecules of NO2. Okay. Per mole. I just didn't write out that the count. Here's molecules per NO2. Multiplied by our moles, less than half a mole. And that will tell me the molecules. Now, I forgot to do that out before. Is there anybody good with scientific notation who could do that for me? It's going to be around 1.2 times 10 to the 23, but that digit might be slightly different. Got somebody running it for me. Sorry, 22. I think that's right for mental math. Or does somebody have a graphing calculator I could borrow and double check my mental math or confirm that I'm... No, I did do that wrong. It's half of that, which should be about 3. There we go. Okay. And I'll double check that number in a second and update it. Okay. I just I did all the math out, forgot to do this last one, and I will double check in a second, but all the layout is correct. It's just punching it in. Okay? So you've seen lots of ways to rearrange. 2.91, so it's close. I went 3.0, I was slightly high. Thank you for doing that for me.